Okay. Let's get the slideshow set up from the current slide. Now, during the last class, wait till the slideshow comes up. I don't know why it does this. It's so aggravating. PowerPoint, I had it all set up to load, and it takes this long for the screen to show up. Okay. And then once the screen shows up, I have to change it. And then do 3 function F10s. And hopefully it will show up again. Oh, it might help if I turn on the projector. I don't know why the projector can't turn itself on. I mean, it knows I'm trying to teach. Just lousy equipment, I guess it is. Okay, it's coming on. Sorry about that. I didn't realize it was off. Okay, last time I had said that maybe we'd be ready for a Chapter 5 test, but then when I went back to look at what we've done in Chapter 5, basically, we started out talking about the fundamental theorem of calculus part 1 and 2, found out y'all had already done part 1, so we just did part 2, and there's just a little bit on that. Net change of integrals, rate of change, and then substitution method, and then a few further transcendental functions, and then we're not going to test you on exponential growth and decay. So really, there was, I can do you a special test on Chapter 5 if you want, but it's going to be, what it would turn out being would be probably 2 questions on 5.5, 2 or 3 on 5.6, at least 3 on 5.7, and maybe 3 on 5.8. Okay? Do you want a test that covers just that? I don't have it made out, but I can make it out. It's not that bad to do. Say that again? Yeah, that's what I was going to say. The option is just to wait until after Chapter 6. And Chapter 6 is a fairly short chapter, and we can do 5 and 6 together. Which would you prefer? I'll go either way you want. You do want 5 and 6 together? Okay. Huh? You'd rather have them separate? Okay. I will make up the test hopefully this afternoon. I started to do it Wednesday or Thursday, and I thought, I will look through. I think I can find enough questions that are decent questions. I've told you before my displeasure with the PowerPoints from this text. That's it. I mean, I blow it up. I do various things with it. But if you think I'm disappointed in the PowerPoint, I'm really disappointed in the test bank. It's a sorry test bank, but they have a lot of questions. I can find enough good questions in there. But some of them, they jump way out into something we haven't talked about at all, but I'll try to avoid those. Okay, so nevertheless, I'm not going to test you on this. Now, a guy in my next class found this. He noticed it. I'll point it out to you in a second. You don't always see it, but if I move the cursor down here, oh, you can't see it now. I'll show it to you next time. I found a shortcut to do some of the things that takes me a few fewer keystrokes than before. We started talking about this last time, and this is actually the figure for example 1. This is a picture of E. coli bacteria. Are they good, bad, or indifferent? Okay? You'd be in serious trouble without them. They're bad if they're out of place. Where they belong, the human intestine. Okay? In the human intestine, they do a lot of good for us. Okay? However, if you ingest them by mouth or through blood, really bad. Okay? So they can cause a lot of trouble and this is what the problem is. I don't mean to make this too negative. It says in the human intestine. is found in any mammalian intestine. In other words, any mammal's intestine, you'll find E. coli. It's a good thing. That's where it belongs. However, if you happen to pick it up and get it through your mouth, very bad thing, because your stomach and your the upper part of your digestive tract is not equipped to handle E. coli. They live fine especially the large intestine, maybe some in the small intestine, mostly in the large intestine. That's where they belong. Take them in somewhere else, you got problems. You got some pretty serious problems because we're not set up for them anywhere else. Actually, I've heard this. I don't know for sure if it's true. Could you drink rattlesnake venom? You can. It's just a protein. It probably wouldn't taste good, but it wouldn't necessarily make you sick. But you put that protein in your blood, no, your digestive system has to break down the proteins into amino acids, and then you can use them. But if you inject the protein directly, you're in serious problem. So, same thing here. They live fine in your large intestine. They don't live well in your esophagus, your bloodstream. You don't want them there. So, bacteria, they're good in the right places, and they're terrible in the wrong places. So, and I started to say this, and I probably shouldn't, but I do. Well, sometimes when people are doing organic farming, gardening, and are using, and it's a great thing to use, waste product like animal waste, like cow manure, pig manure, chicken manure, as the fertilizer source. It's a great fertilizer source, great for the soil, but you don't want to get that on your food. Okay, so you wouldn't want to use it in root crops like radishes, rutabagas, turnips, carrots, things like that. Not the best place to use that kind of organic fertilizer. There's other kinds you can use, like leaf mulch and stuff like that. Fine, no problem there. You just have to be very careful. And sometimes when, things that grow close to the ground, like lettuce and cabbage and things like this, if you're using manures, you better be careful and make sure you wash them very, very well. So that's sort of a downside of some, we had a neighbor, they ran a big dairy, and the guy's wife did the cooking for the workers at the dairy, so they come in from, if you've ever been around the dairy, they are nasty places, okay? The cow barn, and, they got on the boots, so they would come into their house and, eat their lunch every day and stuff. She had a little kid who, crawled around on the floor. He got a pretty serious infection because kids pick up things off the floor and put them in their mouths, and they probably brought in a little bit of cow poop on their shoes, and either his toy or whatever, it made it into his mouth. He was one sick young'un. Okay, so be very careful. And they grow by exponential growth, and that's what the next problem. This is an example of E. coli growth. This is an example. I said I wasn't going to do this, but I'm so used to doing it. Growth of E. coli population. If it starts at 1,000 may be something that wouldn't really bother you. Okay? And maybe 2 hours later, it's barely 1,700. It still might not bother you. 4 hours later, it's up maybe 4,000 or 5,000. That may be pretty bad, but then another hour and a half or a little bit past that, you're up to 10,000, and from there, it takes off. That's exponential growth. It's going up and going up fast. It doesn't take but a few more minutes until you double that again. It's just amazing exponential growth. Start slow, but then really skyrockets. This isn't E. coli, but it's the problem with having food out too long. I know big meals like Thanksgiving and stuff like this, lots and lots of food sitting there on the counter, and then after you're sitting around the table talking, enjoying each other's company, and the longer that food sits out there, for a while, no problem at all. Because there's bacteria everywhere, okay? And usually no problem at all, but if it sits there too long, suddenly there's a ton of bacteria in there. You better throw that out or be very careful and eat it really, really well before you reheat any of that. Okay? Just examples of exponential growth, and we'll also do with decay. This is talking about differential equations. That's a different course, so I'm just going to skip right on over that one. Here's another one. We talked about bacteria. This is a, oh, I'm sorry. I thought this was a different problem. This is a computer simulation of radioactive decay as a random process. The red squares are atoms that have not yet decayed. The white squares are ones that have decayed. The fixed fraction of the red square turns white each unit of time. This is radioactive decay. Starts out with a full population, and then in time it's decreasing and decreasing. Now its curve goes the opposite way from, not quite, but close to it. Here's the example, and again this is differential equation, so I'm going to skip that. And this is an example of radioactive decay. Okay? Now this is a very slow radioactive decay here. Oh no, this is radioactive. This is just another example of how you use this decay, but not radioactive decay. My wife used to have pretty bad headaches, and when she did, she popped her ibuprofen. But she found it was far better to maintain a level of ibuprofen than the headache to come back. She's not having nearly as much problem nowadays as she did. I don't know why, but for a while there, she had pretty bad ones. So she was taking, I thought, way too much of that. But this is what happens when you take some type of medication. This is penicillin, which usually you get through a shot, but I don't know, I guess they do have pills or something. But when you first take that, you might have, better than 400 milligrams in your system. Now let's just say that the effective would be, well wait, I'm sorry, this is showing something else. The effective might be 100 milligrams or 200 or whatever, okay? After 2.6, and this is in hours, after 2.5 hours, then your amount of penicillin in your system would fall below that because your body is using it or expelling it, okay? That's what your body does. It either uses it or it spits it on out. That's a sort of a foreign substance, okay? So if, say, this were ibuprofen and it started out this way, and this is when the headache came back, then she wants to take another one and pop this up again and do this. And that's why they'll say every 2 hours or every 4 hours, that is the recommended dosage. Now, if you don't need it, don't take it. But, to maintain the level in the bloodstream, basically what you do is you do like this, and you're guaranteed to always have enough to be effective in the bloodstream. Now, usually with penicillin, that's trying to knock out an infection, so hopefully you've knocked it out after one dose, but if not, then you get a different dose. You don't take that forever. Why wouldn't you take penicillin or something like penicillin repeatedly? You know why? Then you're helping the bugs, the bacteria, the viruses build up resistance to it. So you want to take it the full dosage. If you get a prescription for an antibiotic, you take it because you need that level until you're sure you wipe them out. But then you don't keep taking it forever because then the bugs build up a resistance to it, and then you wipe it out for the next person who catches it from you. Your bug that you gave to them, that same medicine won't work. So with antibiotic, you have to be pretty careful. This is not so much math. This is other stuff. But this is like exponential decay. That's a exponential decay. It's not radioactive decay, but it is exponential decay. Now, when you have exponential growth, then you deal with a concept called doubling time. Now, you're not responsible for this. I'm just showing you this because this is it. If P of T is P0 e to the kt, that's one we had from the last class, as long as K is positive, then the doubling time for this is log 2 over K. In other words, you're waiting till this thing gets to be twice the original amount. So 2 times that, if you solve that for the time, it would be log 2 over K. Now, give me a K, make up a number. 10, okay? So let's say it's going to be 10, not quite hours, but we'll pretend that's it, okay? So, if you got a calculator, take the, in fact it definitely isn't that, take log 2 and divide it by 10. Got a calculator to do that. Because by choosing a 10, that's going to be a huge number here, so your doubling time is going to be pretty small. L into natural log of 2 divided by 10. Be sure you close that parentheses on the first one. Log 2, close parentheses, divided by 10. Say again? Say that again. 0.069. Okay, 0.069. That's going to double in that many, and if T was in hours, that would double in 0.6 or 0.06. Okay. That would be about every 4 minutes. Okay. It's going to double every 4 minutes. If you get that bacteria in you, you're in pretty deep trouble. Okay. Now, let's take a little bit smaller, like maybe 1. What is log 2? LN2. Second? 0.692, okay? So multiply that by, that'd be 3.6 minutes, okay? Let's do like 0.10, 0.1. So log 2 divided by 0.1. Okay, so that'd be about 7 hours or 7 years or whatever you're dealing with here. That would be whatever units you're dealing with. And that would be a sort of a more reasonable. For instance, right now, does anyone know what the savings rates are? If you put money in a savings account, what kind of interest rate do you get? It's pretty pathetic. Yeah, it's a point. It's what? Okay, let's just say 0.5%, okay? So let's do that. 0.5% would be 0.005. So log 2 divided by 0.005. Well, that's sad. Okay. If you were to put $1,000 in your savings account today, and if it was pulling 0.5% interest, you could leave it there 100 and how many years? 38. 138 years, and you would double that to 2,000. Pretty lousy savings rate. Okay, now let's do this one. What is your rate on your credit cards? Do you know that? Second? Okay, 0.2. Okay, about 20%. So let's do that. If you do log 2 divided by 0.2. Let's say you had a $1,000 bill on your credit card. 2.46, 3.5. Okay, 3.5. That means in 3.5, and if that's per year, I don't know if that is. I doubt if it is, but in 3.5 years, you would double. You would owe $2,000 if you didn't pay anything. The thing is, it's compounded, so I bet you it would add up faster than that. So if you see savings 0.5, 130-some years for it to double your credit card, actually it's probably closer to rather than the other 0.2, but it could be 0.2, but you see, they get you. Okay. That's what we mean by doubling time. Okay. Other things that expand by exponential growth are, I believe this is a computer virus. Are y'all familiar with it? Sapphire? It was quite a few years ago. And these were the number of host computers that were affected by Sapphire. Basically, it follows the technological population. Just about all the U.S. and southern Canada was, this desert southwest in Mexico, there are not that many there. Brazil, this is Brasilia, which is the capital, is in here. Sao Paulo and Rio de Janeiro are down here. Argentina, those areas here. Europe, of course, all of Europe. Some of the Middle East, and the eastern part of China. Western part didn't so much. This included the Soviet Union. The population in Australia is mostly along the coast. Brisbane, Sydney, Melbourne, Perth maybe, or maybe it's okay, I don't remember exactly. South Africa has a few areas. So in India, India has pretty good. But those were that. Places without computers, it's not going to spread very much. So other things spread by exponential growth, not just pathological viruses in us, but computer viruses as well. Okay? And here's an example of the doubling time. Let's see, I don't know which one this is. These are in seconds. So this would probably be something like bacteria or something like that. You started out with 4 at time 0. You would double that to 8 at times 8.5 seconds. Double that one in another 8.5 seconds. So that gives you 17 seconds out here. It's doubled again, and it's doubled again from 16 to 32 in another 8.5 seconds. So even though it had a level of only 8 after the first doubling period, after 3 doubling periods, you're up to 32. Exponential decay. Growth. Okay. That's an illustration of doubling time. And it keeps going that rapidly. In fact, it gets faster. Okay. Whereas on the other hand, when you have decay, as in medications in your body or radioactive decay or something like this is radon 222, which is a radioactive gas. I don't know if you've heard about it, but it can be in any home. It could be any place, but homes are the place where we worry about it the most, because that's where we spend our time. Its half-life is close to 40 days, okay, 3.8 days. So if you had 1 gram, milligram, whatever it was, these one small amount, then in just less than 4 days, you would only have half that much. And then in another 4 days, you would have half that much again. Okay, well, this is half that much would be 2.5, so it would be a little bit longer. So it does decay away. And you might think, well, why do we worry about it? Because we're always getting more of it, because it's the decay product of radium. And radium exists, wherever you find radon, it had to have radium there. Radium's a decay product of, ultimately, uranium. If there's a trace amount of uranium somewhere, it's going to decay. The trouble is, radium is several hundred years half-life. Uranium is probably even more than that. So if you have a little bit of that, it's always going to be decaying. And as soon as it decays, you've always got a new source of radon. So if you've got a source, you're going to have problems with it. The thing is, it does cause lung cancer. So usually you want to test your house for radon to make sure you're not breathing too much radon gas. So half-life, very similar its formula, again, is, what was the one for doubling time? It looks the same way. Here's the difference, though. For exponential growth, the K is always positive. For exponential decay, it's negative. Okay? So, same formula, but if you take log 2 and divide it by a, there's something that doesn't seem right here. Make sure they are saying it right. Yeah. The time it takes it to decrease by a factor of 2. So really it's the same thing, except actually the K is still positive, but you just have a negative sign in front. And so the same time it would take to double, now it's taking to half. And that's what the previous slide was showing. So the formula is the same, log 2 over K. Was there something it's all right to, okay. I thought maybe there was something you wanted to add to that. If there is, please say it. You know, it's fine. Have you ever heard of carbon dating? It's like Match.com. No, it's not that kind of dating. This is how you're aging things like fossils. And this is the guy, American chemist Willard Libby, back in the early 1900s, developed this technique for determining the age of fossils in 1946. Okay, determining the age of fossils. He was awarded the Nobel Prize in Chemistry for that work. Took him 60 years later before they awarded him. So he was 52 years old, which is, he was still young enough to use that really well. Lived to be another 20 years after that. Since then, the technique has been refined considerably. But anyway, what does every living thing have in its body? Whatever body that might be, a plant, animal, bacteria, whatever. What does every living thing have in every cell in the body? Carbon. Every cell in a living thing has carbon in it. Now, most of the carbon in all of nature is carbon-12, okay? The stable isotope of carbon, 6 protons, 6 neutrons, 6 electrons, carbon-12, okay? Now, up in our uppermost atmosphere, where a lot of that cosmic radiation is hitting the Earth's surface, Earth's atmosphere, when it does, it sort of messes things up, and carbon that might exist up there, it gets energized and sometimes forms carbon-14. Carbon-14 is radioactive, okay? So, but how do you get your carbon? Okay, actually when we breathe in oxygen, we breathe out carbon dioxide. So we actually lose carbon by breathing. Eating, yes, when you eat anything, as long as you're not eating rocks, okay, but eating plants, eating animal, eating whatever, you're intaking carbon, okay? Now, those plants were living not too long ago. No matter how old your food is, it wasn't that long before they were living. So most of the carbon you're taking in, you have mostly carbon-12, but you're taking in a little bit of carbon-14. Not enough to hurt you. It's radioactive, but it doesn't hurt you, okay? But in time, that decays away and becomes carbon-12 again, okay? And that sure doesn't hurt you. So, a dinosaur that lived how many thousands of years ago, it ate leaves and stuff, and it took in carbon-14, But once it died, it wasn't taking in any more carbon-14. And that carbon-14 that was in its body was there in a very small percentage, right? But then over time, the carbon-14 decayed away into carbon-12. So after a while, there's very little carbon-14 left. That's how they do carbon dating. They take the fossils that have been dead a long time, measure the carbon-14, fit it on the decay curve, and then figure out how old the fossil was. That basically is a simplistic approach. They have refined it a lot. Let me see. Let's go back to this. Now, this is not talking about carbon-14, but let's just imagine it was. This is radon. Let's just imagine that you have a certain percentage of carbon-14 in every living thing, and then it's decaying away, okay? Now, it's decaying away like this, and it really flattens out here, right? It never gets to zero, ever, okay? So, if you found that fossil and it had this much carbon-14 in it, okay? This much. You try to fit this curve to see where that is, okay? Well, it's right there. You say, that fossil is more than likely 7,000 years old, okay, or something. I'm just making something up. But notice it's so flat out there. If you miss something, like your extraction technique or something else is off a little bit of error here makes a huge error there. So they never can get this very close. They've got ways to make it better than what he first discovered, but it's really, when you get on the flat part of the exponential curve, you can be off a little bit here and that can throw you off a huge amount of what you're trying to determine. So they're never precise, ever.
How were they able to observe carbon-14
How are they able to what?
Did it say like the carbon-14? Did you say
Okay. All they do is detect how much of it's there. They know the curve. Oops. They know the curve. This is not that. This is radon. But they know the curve for carbon-14. Okay? And if they detect, here's where another error comes from. They're assuming that many years back, you had the same percentage of carbon-14 in the atmosphere that you do now. They don't know that. But they're assuming that's true, figuring that all the activities that puts it in the air in the first place are still similar. That may not be safe, okay? But that's an assumption, okay? But they know, and if they measure a certain amount, then they read how many years it would have taken for it to decay down to that amount. They're assuming it's starting the same place it is today. They may be a little wrong there, and if they're a little wrong there, but the biggest error comes if their extraction techniques and their measurements and stuff are a little bit off here. That could be a huge. So that's why when you read something in the literature, they can only get it within a few thousands of years. They can't get it. Oh, this was 12,474.3 years ago. No, they can't do that, because they cannot get, they say, within a few million years of this, so that's the best they can do. Okay, so it's not precise by any means. All right, I don't know why this one's here. I remember it from before, but let's read it and see. These are, and this is what they're doing, okay? These are some paintings found on carbon etching. What they did was they burned their fire, and they had a stub of wood left over with, the soot on the end of it, and this guy was a pretty good thrower, so he took this and drew the bison here, okay? This was in a cave in France, I think. Lascaux cave mural. What they've done is take a little bit of that soot that he drew this with, he or she drew it with, and then measure the carbon-14 in that, and then go to the table, find out about what time period and that's how they're able to do this, because they figured that tree was living just shortly before they burned it, right? So, certainly not too far. Oh, this may be, yeah, here we go. This is a carbon-14. I was using radon. I forgot they had this one here. Okay. This is the decay curve for carbon-14. There's the formula for it. Okay? On your calculator, you do log 2 divided by 0.000121, and that gives you the half-life for carbon-14. And that's a huge amount. Log 2 divided by, don't use the sign, 0.000121. What do you get? So 5,000 years for it to get down to half that amount. So the older something is, now this curve goes like this, and it never reaches 0, so don't think it's going to intersect. It doesn't. It's going to flatten out and flatten out. So if you get down in the flat part here, now this is 15,000 years ago, okay, that's still, you know, if you have a little error here, you can have a fair amount of error here. When it gets flatter, same little error could be a huge error there. So if only 15% of the carbon-14 remains, the object is approximately 60,000 years old. See, approximately 16,000. It came out from 15,700, but guess what? A little bit of error here might make a big error there. So we say about 16,000 years old. So that's a better illustration of it. Okay. Here's another one, and this is what I was referring to before, compound interest. Okay? If P0 are deposited in an account earning interest at an annual rate of R, compounded M times a year, then the value of the account after T years, this is another example of exponential growth. Okay? And this factor here, the entire factor here, is called your yearly multiplier. Okay? And the more years you keep in there, then the more it grows. And the larger the number of times it multiplies by year. So if it's once a year, this is a 1 here, that's a 1 there. Fairly simple formula. If the compound answer is twice a year, semi-annually, it's a 2 here and a 2 there. Quarterly would be a 4 here and a 4 there. Monthly would be a 12 here and a 12 there. Daily would be a 365 here and 365 there, 365 and a quarter, or something like that. So that would be what you do. The thing is, it doesn't make a lot of difference once you get past quarterly or so. It's not going to grow that much faster, but that's your multiplier. Did we skip a slide? No. Okay. Here is, and it's sort of sad, you think it's better to do compound daily. If you compound annually, if you started with $100 and 9% interest rate, which is way better than what it is now, in 1 year you would have $109. If they compounded quarterly, you get another 31 cents. If they compound monthly, you get another 7 cents more than that. Weekly, another 3 cents more than that. And daily, only 1 more penny than once a week. Okay? So guess what? If they do it daily as opposed to annual, you'll get another 42 cents. Okay? At the end of the year than you would. Same interest rate, but just how often they compound. So it's going to take a while before you can buy lunch, you know, with the difference. But, you know, every little bit helps. Okay? But if you do the same thing with the 24%, which is much what credit cards are, try that. And they don't ever do annual. They do daily. I think they do daily. Okay? So they don't even start up here. They start down there. and if that was a 24, then this is going to be at least $125, $130 there after 1 year. So it's not going to take them but a few years before it's doubled. If you know, it would not be $100; it would be $200. You know, it goes up pretty quickly. Okay. Now, here's another formula, and this is basically talking about what we just did. Remember, it had a form of 1 plus 1 over n to the n. As you change the n's here, at first it made a little bit of difference after a while, but after a while it got really close to the same thing. The reason for that is the number e to the whatever, that's going to be the limit as n approaches infinity. That is the value e. So when they say compounding continuously, it's e to this. And the formula for that is this one. I'm just giving you this because this is stuff that you do run into in everyday life. So I wanted you to be exposed to this. So e to the x would be the limit as n approaches infinity of 1 over 1 plus n to the base of the n. And that's going to give you e to the x. Well, okay. That's how you find e. E to the x would then be put an x in here. So whatever rate this is, that was your rate. Okay. So put it in, and that's your exponential function. So there is what you do if you're why they chose capital M, I'm not sure, but oh yeah, that's your multiplier. And if the multiplier was going to infinity, in other words, you're compounding continuously, then that's e to the r. Okay? So if you go back to, well, and that's what it's really inexcusable to me that any bank doesn't compound continuously, because otherwise you have that really complicated formula. If they just did it continuously, you'd have this. It's not costing them that much more, but they don't want to give it up, because this would be so simple to plug into any computer, and you can always know exactly how much you are without having to do so much extra work on it. Of course, computers do them all fast. That is compounded continuously. That's your formula, much simpler than what it was before. Now, you can do all sorts of things with that then. For instance, probably y'all will be parents one day, and if you're trying to set up, say, savings account for the kids' education, this is called the present value of T dollars received in time T, especially if it's compounded continuously. The present value would be, if you put this much into the account, how much will it be? Let's see, I may be I'm saying that a little bit wrong. If you want the amount at the end to be this, how much present value do you put in to make the final amount? Okay, that kind of thing. You can do all sorts of things with these exponential functions. Or if you know how much you can put in right now, what will its future value be? You can do that. So the present value of an income stream. Okay, this would be it. I'm 65. Okay. I hope my health holds out, and I'm going to retire at 70 if things work out. And then at that point, if I took all the money that I have through anything, and my pension and all this kind of stuff, and then, but let's say not that, but everything else that I've saved up, and then start pulling down on this, how much how long can I go? You know, what would be the present value, you know, that's within your doing an interval. So, wow, you can do so much with this. How long could I take this much out of what my current savings are at age 70? How many years can I live on that? You can do all these things with exponential functions, integrations. Yeah. Okay. All righty. If you listen up on this, you know these are all being recorded under, yeah. So if you listen up, you can catch the rest of it. All right. That by itself means almost nothing. I'm not going to go into this. We're almost at the end of the period of thing. In fact, I don't even see where that. Oh, there it is. That's the very last. It's a part of the proof of the previous theorem, so we won't get into that. All right. Let's see what this is. This is just a slideshow showing you illustrations of exponential functions and logarithmic functions, stuff like that. This is the graph of the last equation. 1 plus n. So again, you almost need to do the proof to make that make sense. That's the end of chapter 5. And again, okay, I'll try to have ready for you next time. I had planned to do it this time, but then I thought I want to find out if y'all want to do it. What I'll do is probably 2 questions on 5.5, 2 on 5.6, 3 on 5.7, and 3 on 5.8. That'll be your test. I'll try to have that ready for you on Wednesday. And that'll give you a score earlier in the term, and you won't have to pile it on with everything else. Let's go back and back and go to chapter 6. Chapter 5 was still wrapping up integration. All those examples are things in integration. And by the way, there's because you're not responsible for this, I'm not making any homework assignment in 5.9, but chapter review questions, since we are dealing with, let's see, what was the first section I said we would cover? 5.5. That was Fundamental Theorem of Calculus, Part 2. I'll just give you roughly on these review exercises. This starts somewhere after your definite integral. I'd say somewhere around exercise 17 or so. Now, you're not responsible for differential equations, even though we talked through some of those. But the things on substitution, 39 to 42, certainly that. 40, and again, the odds, 43 to 91, any of those would be probably pretty good ones to look at. And let's see, we'll go up to it's hard to see where in here to stop. Certainly don't do anything with the radioactive decay and stuff. So I would say don't go much further than maybe 113. You may not even do all those. But anyway, let's go on. Well, the next thing is Chapter 6, applications of the integral. Chapter 5 was calculating the integral, so we'll cover from fundamental theorem of calculus. Why is this not loading? Okay. Part 2 through transcendental, some of the transcendental functions. Okay. Whatever sections I said those were. One problem, well, I'll figure that out. All right, we're in, still recording, so let's go from current slide. Why does this take so long to load? I don't know. Okay. I have to hide presenter view, and do this, do that, and do that. Okay, I think we're back. All on the same page. Now, I don't know if you've heard of, seems like this is a very medical seeming class right now. We were talking about bacteria and that kind of stuff, and drugs and penicillin and stuff. Here's another medical application. Magnetic resonance imaging, MRI. Now, in your book, it's not quite the same picture. You actually see the vein. This is the machine that takes the picture of those veins, okay? This is the picture of the vein over here, I guess, okay? And veins in the patient's heart, the MRI scanners use the mathematics of Fourier transforms to construct 2- and 3-dimensional images. Now, I don't remember for sure which kind mine was, but I had what they call a little heart flutter. And one doctor wanted to do an invasive technique. My wife said, absolutely not. So we went to see a cardiologist. He said, we can just give you a little radioactive isotope in the vein and we can take pictures of your heart and see what it is. And far less invasive. And it may have been a machine that was somewhat like this, but they showed me pictures later. They had a picture of my heart and the computer sliced it this way, sliced it that way, sliced it that way, and everything looked really healthy. Of course, they didn't have to do any real slicing, but boy, it's amazing what they do using Fourier transforms. Now, we're not going to do Fourier transforms in the course, but since it's mentioned in the book, who in the world is Fourier? French mathematician. Actually, was associated with Napoleon, by the way, so you could go into that if you wanted to. Who was he? How did he develop these Fourier transforms? Or how are they used? And there are many ways. MRIs are just one of the many types of ways that different types of math are used. Without math, all these equipment would be worthless because you wouldn't have, you might be able to do the stuff, but they wouldn't be able to interpret without the math. All right, here's I don't know if we'll get this one to zoom properly. Yeah, I think we will. Okay. One thing that we do, applications of integrals, is taking areas under curves. We've already seen that. But then there's other things we can do is take area between curves. Okay? And this is U.S. renewable generating capacity. And this is, I don't know if you remember when we had not the Great Depression, you wouldn't remember that. I don't even remember that before I was born. But the Great Recession, okay? It happened around 2008, 2009, sometime in there, in fact, 2007, 2008, around in that time. And by 2010, they were trying to figure out a way to get out of it and to help it. And we had, I don't know if you remember, it was called the stimulus packet, okay? And if they had used, this is one of the graphs they did use, this was the actual U.S. Renewable generating capacity, and it had been increasing, but then when the depression hit, the odds are it was going to decrease. I mean, still increase, but not as a greater rate as it had been doing. So they were saying, what if we use the stimulus package to increase our generating capacity of using renewable resources rather than maintain or letting them decline with the recession, actually increase them? What would be our generating capacity later? Well, this is an estimation, and this is, based on that, what the thing would be. So how much excess will we have if we applied the stimulus to this particular, a certain amount to this particular industry? So you use calculating the difference between two curves, the area between two curves. That's an example of what you would have. It's not actually a problem, it's just giving you a background, okay? A real-world type application for that. Now, a couple of definitions here. I don't think, okay. Suppose we're given two functions, y is equal to f of x, like maybe this one, the blue function, and y is equal to g of x. So I'm sorry, I said it backwards. F of x is the red function, g of x is the blue function, such that f of x is always greater than or equal to g of x. We call such a region vertically simple. In other words, you make a change here, and this is vertically simple. There's nothing compounding or confusing this. You have a curve up here, a curve down here. Just take the difference between the curves, and you got the difference in the area. A vertically simple curve. Okay? Now, if you have that, then this is how we determine the area between the curves. Okay? And it's what I've been talking around. Here's the actual formula for it. So let's say we had f of x is the upper curve, g of x is the lower curve. The area between the curves is the difference between the area under the upper curve minus the area under the lower curve, then that would be the difference between. But guess what? Integration is a linear process, so you can take this, and the difference of two integrals is, as long as the limits are the same, is the same as the integral of the difference. So rather than taking the difference of two integrals, you can subtract the two integrands from each other and just do one integral. It gets down to which is easier. Okay? If these are both really easy to calculate, but the difference isn't as easy, do these. But most of the time, the difference between that is going to be easier to calculate one integral than two. I always swear that, but most of the time that's going to be the case. Okay? Now, here's some examples. There's one figure, I'm missing figure 2. I don't see figure 2 here. So, I guess they left out figure 2. They didn't have figure 2 in the previous. But these work just as well. Okay. Basically, this is illustrating exactly what the last thing said. Now, let's see, can I get all these on here? Woo, I think I can. Just barely, but I think I can get them all on there. Okay? Now, let's start. Here's your function f of x, the red function. Okay? The area between a and b under the curve there of f of x would be the integral of f of x dx. Forget about g, it's not even important here. Okay? But if I were going to subtract from that the g part, then that leaves me just this part here, and that's it. So this is saying the integral of f minus g dx between a and b is the same as the integral of f of x minus the integral of g. That's showing exactly what the previous slide was showing symbolically. Okay. Now, this, I think, may be example 1. Is it? Yes. So let's do example 1. There's not really any. Well, I'll blow it up just so you can see that the equations are the same. Find the area of the region between the graphs of the functions f of x is equal to x squared minus 4x plus 10, and g of x, which is 4x minus x squared, between 1 and 3. Okay? So that's the problem. And of course, when I go to write, say again? You got it? Okay. Now, what I was saying before, you see if I get the cursor down here near the bottom, I can actually, yeah, it's sort of a shortcut. I can get to my pen a lot easier. What I can't necessarily get to is the color. But I think that, you see, I want to go right here and hit there, but if I hit there, it's going to end the slideshow. So I'm going out here. I think that's also black, but if it's not, it's dark enough. So I will go there. And so let's do it. Find the area of the region between the graphs of the two functions, f of x and g of x. Okay? What would that be? Integral from 1 to 3 of x squared minus 4x plus 10 minus 4x minus x squared. Okay, now I'm doing it the long way. Dx. Okay? That will be the integral from 1 to 3 of x squared minus 4x plus 10. You don't have to take this many steps if you don't need to. Minus 4x minus a minus is plus x squared. Okay? And then finally, that'll be integral from 1 to 3 of, combined like terms, that will be 2x squared minus 8x plus 10 dx. Second? Factor out of 2. Excellent. 2 times the integral from 1 to 3 of x squared minus 4x plus 5 dx. What's that? Antiderivative of x squared is x cubed over 3 minus 2x squared. Yeah, or 4x squared over 2, x, and 4 over 2 would be 2. I did 2 steps at once, sorry. Okay. Right. I thought that's what you were getting ready to say, so I jumped ahead and said it. And then last, plus 5x. Evaluate that from 1 to 3. And that would be 2. I say 2 and write 3. Okay, here's where this comes a little handy. Eraser, eraser. Whoops. Yuck, I didn't want to do that. Okay. Pen. Okay. That will be 2 times, when you put a 3 in there, what do you get? 9 minus 18 plus 15 minus 1/3 plus, minus a minus is now plus, right? 2 minus 5. Okay? Oh, if it wasn't for that 1/3, this would be a pretty decent problem, wouldn't it? Okay. So let's do our plus 15 minus 5 will be a plus 10. Okay. So that will be a 19 minus 18 is 1. Plus 2 would be 3. Minus 1/3, that would be 2 2/3. 2 times 2 2/3. Well, 2 2/3, that would be 2 times, is that 8/3? I think it is. Yeah. So that would be 16/3 or 5 1/3. Okay, whatever. Okay, let's see. I was doing it fast. Yeah, 16/3. That's what they got. See how that works? All right, good deal. Okay. We cheated. We just looked at their figure, didn't we? What you needed to do was make sure that f of x is always greater than or equal to g of x within those values. And basically, the best way is to put it on your graphing calculator if you've got one. Do you have a graphing calculator? Okay, yeah. Put them on there, graph them at the same time, make sure which one's on top. Here's the problem, though. If this would have come down like this, and this would have gone up like that, and you had some place where there's overlap, you can't use this rule. You have to split it into 3 different pieces then, or however many different pieces to make it work. But what you see, f is always greater than or equal to. They can even come down and touch, but as long as they don't cross. If they cross, you've got problems, okay? But if they touch, you're fine, okay? Or if they stay separated, you're fine. One is always greater than the other. Okay. Now, it says, before continuing with more examples, we note that equation 1 remains valid whenever f of x is greater than g of x, even if f of x and g of x are not assumed to be positive. Before this, when we talked about areas under functions, under curves, we always had to assume the curve was positive. Never got down here. But now we don't need that anymore. And unfortunately, they don't have the next figure here either. I'm sorry. The slide set doesn't have it, but if you got your book, you can see that f and even g, or f and g, can both be negative. You can still do the area between curves using that. Okay. Let me clear. Let me see. All right, let's do this. If this was f of x, yeah, you can take the area under the curve from there. No problem. Okay, I'm going to go to a different color then. Okay, yeah, but, okay, what color you want? You pick one. Blue? Light blue or dark blue? Light blue, got it. Okay, if your function had done that, you had trouble finding the area under this curve, because here the area is positive, there the area is negative, and there the area is positive. So then you would have the net area. That net area may be 0, it may be slightly positive, it may be slightly negative. But you usually don't think of areas being negative. And if you mean the total area, then you have to do this one, then you do this minus that. You have to split it into 3 pieces. So that's why you couldn't. Now, but if you said the area between these 2 curves, you can do that now. Because as long as the f doesn't get below g, you can do it. Even though g down here is negative. Because you're doing that minus this, that just gives you a bigger thing. That gives you a larger segment, rectangle. But the length is still f minus g. Okay. So that's fine. And what's more, you could even do it. You want a different color? Second?
Sure. We do green.
Green. Okay, let me do the dark green. Okay. What if your other function was this one, and you wanted the area between these two. You can still do that, even though G, H, or whatever you want to call this one, is always negative, because you're doing this minus this. That is still a positive quantity. So that's what they're saying. You're not limited, whereas before, if you're just doing the area under one curve, you usually make sure the curve's positive. Now, it doesn't matter if one, the other, both, or mixed are things, as long as they don't overlap each other. If they overlap each other, you got the same problem you did here. Okay. That's what they're talking about. Okay? Okay. Now, so that then, okay. The area between any two graphs, it doesn't matter which, as long as F is always greater than or equal to G, then you can do this. Whether F is positive or negative, G is positive or negative, in the limits, it doesn't matter, as long as the one on top minus the one on the bottom. And as long as F is greater than or equal to G, you can do it. Okay? So nothing changed from before. It's just that you don't have to even assume they're always positive. What you have to assume is this quantity is always greater than or equal to 0. This quantity can't be negative. For that to be negative, then G would be greater than F. Okay? So as long as that's fine, you got it. Okay? And here's what they're talking about. This is my rectangle picture. I was saying, how are we doing on time, by the way? Oh, really? Okay, he left really early. What time is it? 10:29. Yeah, very. Okay. It says we've been going for an hour and 11 minutes. We started at 9:30. Oh, yeah, it's an hour 40, actually. Yeah, okay, got it. Okay. Something was not jiving with my brain. I think most of the other classes have been less than this. So, okay. So what we're doing then, if you picture this as your good old Riemann sums, and by the way, Riemann would be a potential paper topic. How do you develop Riemann sums? That would be application of Riemann sums. Any of those would be good paper topics too. What we're dealing with is some upper function F and the lower function G, as long as F of X is always greater than or equal to G of X, but never less than G of X at any point between A and B. Now out here, no problem. What if this kept going down this way there? Out here, but we're only integrating from A to B, so not an issue. Okay. Sorry. Trouble with breathing. What we're doing then, you split the interval from A to B into a partition. Now they did an irregular partition. I don't know why they do this. They don't have to be irregular. I mean, it doesn't matter. But a partition. Why, I don't know. Why did they just make them even? That would have been so much easier to do. But here you split it into 1, 2, 3, 4, 5, 6 partitions. Okay? And from the first endpoint to the first partitioning point there, you have a function. And this is your dx, okay? And your alpha of x up here, your g of x down here, alpha of x minus g of x, that's the height of this rectangle, times the width of the rectangle, your dx. So this is alpha of x minus g of x, dx. There is your area of the rectangle, okay? Now, obviously, that rectangle isn't the same as area between the curve, but it's not far off. This overshoots, undershoots. This undershoots, overshoots. And if you balance those out, it's not going to be far off. It won't be exact, but it won't be bad. And then the next partition, that's a lot better one because it's a smaller interval here. Your dx is smaller. Overshoot, overshoot, undershoot, overshoot. So it's still not bad, but all you have is your dx times your height. Okay, dx times the height, alpha of x minus g of x, that's the height between this point and that point. And if you do these for all of them, then the key here is select the delta x is smaller and smaller and smaller. The dx, delta x is smaller and smaller and smaller, and after a while it becomes a dx, and then you have exactly the area under that curve, or between the two curves. And it doesn't matter, the lower one is always negative. The upper one could have even been somewhat negative, as long as they don't cross. They could touch but don't cross. Now, this is example 2, which gives us a little bit of a problem. Okay? I'll zoom it in just so you can see it, and I'll read the problem to you. Find the find the area between the graphs of f of x, which is your red curve here, x squared minus 5x minus 7, and g of x, which is x minus 12, over the interval from minus 2 to 5. What's that? Yeah, from minus 2 to 5. Area between that. Well, here we got problems, Houston, and here's what they are. Here, f of x is greater than g of x. In this ring, g of x is greater than f of x, and that gets you right up to the 5. Okay. They drew the picture so we can see that. How do we determine that without the picture? You can graph it on your graphic calculator, and that certainly works, but how do you know the endpoints? They showed them to us here. How do you figure out what those places that you have to change your approach? Yes, set those equal to each other. You're absolutely right. Of course, as soon as I go to do that, it's going to shrink, but we can live with that. So we put f of x, x squared. Oh, yeah, that's right. I left it. X squared minus 5x minus 7, set that equal to x minus 12, and solve for x. So how would you do that? Okay, you're subtracting x from both sides and adding 12 to both sides. Minus x. God, that's gracious. Well, let's see. Let me do it down here. Okay. Minus x plus 12. Okay. So this becomes x squared minus 6x plus 5 equals 0. Factor that, and how does that factor? X minus 1 and x minus 5. Yeah, sure enough, that works. And set each of those equals 0, x equal 1 or x equal 5. So that gives you the two places they cross. Now, you still haven't found out which one's on top. Okay? Now, the easy way to me to do this is pick a point outside of 1 to 5. And we're doing from minus 2 to 5. So we know 5 is okay. So let's just pick a point less than minus 1. Less than 1 is greater than minus 2. Easy? 0. I love it. Put a 0 in that one, and what do you get? -7. You put it there, you get a -12. So here you know that f is greater than g. Okay? Okay, here we know they're equal to each other. And if you wanted to, just pick a value in between 1 and 5 to make sure g is greater than f. Like maybe 2. Would that be okay? Okay, so pick 2. That would be 4 minus 10. That would be a -6. Minus 7 is minus 13. And here, 4 minus 12 is...
2 minus 12.
I'm sorry, yeah, 2 minus 12
-10.
is -10. What did I say that one was?
That was a -14.
-4. Okay, so obviously the negative, yeah, g is greater here. so we know how to do our integration. Okay? Now, first, the area between the graphs. Okay? And so what we do then is, on the first part, F's greater than G, so we do from -2 to 1, and we do x squared minus 5x minus 7 minus G. Now, can I skip a couple steps here and make that minus x plus 12? Don't have to put it in, okay. Dx, okay. Still got one more step to go, -2 to 1. That'd be x squared minus 6x plus 5. That's the same thing we had before, so we're happy with that. That is strange, isn't it? Did I do it right? It's still right, okay. Dx, so we can do that integral. What's that? Over 3 x squared. And we're going to evaluate that from -2 to 1. So that will be 1/3 minus 3 plus 5 minus, second? Okay. Yeah, but it would be a -8/3, so minus and minus would be a plus 8/3, right? Okay. And then you have a minus, and it stays a minus, so that would be another plus 12. And then you have a minus, a plus, but that's minus from being the lower limit, but then a minus 10, so that'd be a plus 10. So you're getting a lot of pluses here. All right, so let's do this one first. That would be 9/3, which is 3. 3 minus 3 is 0, and that leaves us 27. All right, 27 for that part. Then the other part, we're doing the integral from 1. Yeah, where did it go? There we go. All right, 1 to 5. And this time we put the G on top, so that would be x minus 12 minus x squared plus 5x plus 7 dx, and that would be integral from 1 to 5 of a minus x squared plus 6x minus 5. Okay? Dx, and that would be x cubed over 3 minus 5x. Okay, evaluate that from 1 to 5. And let's see if I can find enough white space to do it. Only a negative 125 over 3 plus 75 minus 25 minus a minus, which is plus 1/3, right? Minus what? 3 plus 5. Okay. Now, adding this to that would make it minus 124 thirds, which would be minus 41, right? Right? Minus 41 plus 75. Well, let's see. To make that a plus 50. I'm running out of room, so I want to skip as many steps as I can. So plus 75 minus 25 will be a plus 50. plus 2. Okay, that would be 52 minus 41 is 11. So that should be the yuck. What did I do wrong here? Okay. I knew I was doing some things too quickly. Oh, of course. 3 will go into 12 4 times. 3 will go into 4 1 and a third times. Yeah, sorry about that. I was doing 4 into it. Okay. So that was yuck. 52 minus 41 and a third would be 10 and 2/3. And that would be 30 2/3. Now, is that what they got? No, they got 113 thirds. I messed something else up much bigger than this. Let's see what it is. What's that? Oh, yeah, I'm supposed to add those together. You're right. 27, which would be 81 thirds, plus this, that would give me 113 thirds. Yeah, that's it. Okay, yeah, of course. Add those together. Okay. Now, how are we doing on time? Plenty of time? 5 more minutes. Let's see if we can get this next one done. So this is a little bit of a complicated problem. Let's see what we can do. Can we get this all? Oh, we can. Look at that. All right. Find the area of the region bounded by the graphs y is equal to 8 over x squared. That's your red curve here. Y is equal to 8x. That's the blue curve there. And y is equal to x. That's the black curve there. Now, obviously, they don't have their scale 1 to 1. They have 1 to, shoot, maybe 4 or something like that. You know, it looks like about, so things don't quite look right, but, you know, you can still live with it. Now, there's really not any nice, pretty way to do this, okay? It might, you might say, well, will dy's help you any more than dx? No, they won't, okay? So choose which one you're going to do, delta x or delta y. And now the good news is they drew the pictures for you. You really needed to calculate these yourselves, okay? What was the place where these two curves intersect? Well, that you set them equal to each other. Of course, as soon as I do this, 8x is equal to 8 over x squared. Okay. Well, first thing you can do is divide out 8's. Okay, and you have x equal 1 over x squared. And then multiply x squared by both sides. X cubed equal 1. So x is equal to 1. Okay, so that's the place where those two cross. Okay, let's do the next one. Well, one of these is pretty obvious. 8x and x, they touch at 0. Okay, so that one's fine. These out here, 8 over x squared is equal to x. The two y's equal to each other. That gives you x cubed is equal to 8, so x is equal to 2. So that, sure enough, is where that one crosses. Okay. So with those in mind, You then split your domain, the x values, into 0 to x, 0 to 1, and that will then be the blue curve minus the black curve, right? That should be x's in there, 0 to 1. Then from here on out, 1 to 2, you do your dx, but your x's are going from 8 over x squared to x. So that's your difference there. So you break it into A and B, and let's see if we can set up these and go. First integral really is not too bad. Okay, what would that be? Say again? 0 to 1. Yeah, minus x, that would be 7x dx. I think I can almost do that one, okay? Plus, and what's the second integral? 1 to 2, 8 over x squared minus x dx. Ooh, yuck, okay. Actually, that's still not bad, okay? You want to go on and do that one? 7x squared over 2 divided by, from 0 to 1. Plus, now, here's what I suggest on it. What would you suggest on it? Say again? Okay, and what would that be then? I put the 8 on the outside, x to the negative 2 dx. You don't have to do it this way, but I just find it easier. Minus the integral from 1 to 2 of x dx. Why not? Okay. What would this one come out being? It's 7/2, right? Yeah. Okay. Plus, and what does this one come out? 8 x to the minus 1 over a minus 1, so that just is a negative x to the minus 1. That's evaluated from 1 to 2, minus, and what would this one come out being? X squared, evaluated from 1 to 2. Okay? So, say again? Oh yeah, I'm sorry, I forgot my 2. Yeah, x squared divided by 2. Okay? So this would be plus, and what does that one give you? I'll do the 8 out front. Negative 1/2. Okay, minus a minus, which is a plus 1, right? Okay, those are so tricky. Okay, and this one would be negative 2 minus a minus, so it would then be a plus 1/2. Okay. All right, let's see what we got. 7/2 minus 4, right? Plus 8 minus 2 plus 1/2. Okay? 1/2 and 7/2 would be 8/2. That would be plus 4 minus 4 is 0. And this gives you 6. Let's see. Did it possibly come out that easy? Yes, it did. Okay, good for them. All right, good deal. Did that just about use us all up? What's that? Okay. We'll begin at the bottom of page 335. That's integration along the y-axis. Okay? And I've got to find my... Oh, there it is. All right, let's see. Any homework problems here? I'd say any of the odds, do 1 or 3. Probably 5. 7. 9 or 11. And stop there. We'll pick up the rest of those later. Actually, let me back up. Yeah, I think they'll be okay. Yeah. Okay. Good deal. All right. Then I'm going to name this one 6.1. Okay. So let's end the slideshow. Well, let's see. Yeah. Sorry. You wake up. All right. Can't find my cursor. There it is.